Hello guys, and welcome to the final part of the proof of existence of a non-trivial solution of Pell's equation. And at the same time, this is the final part of the final lesson of this course, and my congratulations to those of you who reached the final part. But let's go back to the Pell's equation. And from the previous several videos, we know that there exists a positive integer d and two pairs of integers x1, y1 and x2, y2, such that x1 square minus a y1 square is equal to d, and also is x2 square minus a y2 square. So both of these norms are equal. They're equal to each other and they're equal to d, but this is only the first condition. The second condition also is about d, and the second condition is that x1 is congruent to x2 modulo d and y1 is congruent to y2 also modulo d. The central difficulty of the proof was to have the same d here, and this is what the previous videos were about. And this one will be an easy one. This part will be an easy one because we will transform the existence of such pairs into the existence of the solution of the Pell's equation. Okay, so now as usual, denote x1 plus y1 square root of a as z1 and x2 plus y2 square root of a as z2, and of course consider z equal to z1 over z2. And this is the most interesting number among all present on the board, because we will show that it also belongs to, first we will show that it also belongs to the ring of quadratic irrationalities, and then we will quite easily show that it is the solution of the Pell's equation. Well, but first part, why is it an integer quadratic irrationality? Well, just write the fraction. Z is equal to x1 plus y1 square root of a over x2 plus y2 square root of a. Actually, to be frank, we already did this proof, but I will repeat. This is equal to x1 plus y1 square root of a multiplied by the conjugate of the denominator, x2 minus y2 square root of a, and when we multiply both the numerator and denominator by the conjugate of denominator, the new denominator will be x2 square minus a y2 square, which is actually equal to d. And in the numerator we will have x1, x2 minus a y1, y2 say, plus square root of a multiplied by x2 y1 minus x1 y2 over d. But we know that x1 is congruent to x2 modulo d. So their product is congruent to, say, x1 square modulo d. What about the y's? Well, of course, this is congruent to y1 square modulo d. And what about these products? Well, for instance, x2 y1 is congruent to x1. We substitute x2 by x1, and we substitute y1 by y2 modulo d. So what do we see? We see that both summands in the numerator, both of these brackets, are divisible by d. So from this it follows that, well, it follows that z is equal to, well, some integer x plus, well, x is this bracket here divided by d, plus some integer y multiplied by square root of a. Y is equal to this bracket here divided by d. Thus, it belongs to the ring. And now, since we know that it belongs to the ring, we can use the ring arithmetics to prove that z is the solution of the Pell's equation. Well, just consider z multiplied by its conjugate. We know that z is equal to z1 over z2. And the conjugate of such a fraction, well, let me write it in the original form. Fraction conjugated. And the next step will be to use the properties of this conjugation operation. And just write that, well, we don't change the first fraction, but the second fraction, we just write z1 conjugate over z2 conjugate. And then it is equal to, well, z1 multiplied by z1 conjugate, it's d. But not because this is d, but because this is equal to d. This expression here is equal to z1 multiplied by z1 conjugate. And z2 multiplied by z2 conjugate is d, just like here. D over d is equal to 1, which exactly means that z is a solution of the Pell's equation. And the last question is, why is it non-trivial? Well, let's just recall that pairs mentioned in the beginning, pairs of integer numbers, they are not the same. These are two different pairs. Let me just remove this comma and state that they are different pairs. And when we take different pairs, we will obtain z not equal to 1. This is it. So every Pell's equation for every for every non-square a, so a is not a square of an integer, has a non-trivial solution. But how to find this solution is another, well, even more complicated question, because our proof is non-constructive. We didn't show how to find this equation. We just proved that it is It exists out there somewhere. See you.